Okay, so we're going to walk through this. Okay, I did see a lot of people, which is fantastic, jumping to what we want for the answer, which is great. We want for the answer grams, okay, for our final answer. One of the things that we're going to find when we officially move into that next unit is that that is an incomplete, or the next section of material. Okay, that is not a correct unit. What is wrong with that unit? I didn't specify the substance. Is the substance changing here? No. So we tend to get lazy in these early conversions and drop the substance from our unit. But our unit should always include the substance. Your unit is a measurement and substance. Okay? I'm still going to be lazy. I don't want to write it out. Okay? But in this case, our measurement is grams, and our substance is, what is it? Acid. Okay? Yes?
Just to go into what you're saying with like the substance, whatever, do we have to include like the substance inside the actual equation itself, or like just at the end?
It should be through your actual equation.
Okay.
Anytime you use a unit, you use the measurement and the substance. Okay? So if you remember back before spring break, I think we did the SOMOX, something like that. Did I do that with you guys? What? Yeah, okay, so you, and I only vaguely remember, but we had this massively long, crazy-looking unit, and we abbreviated it down to just the first letter of each of the words in it. Yeah. Okay? That's because we have to use the entire unit. The entire unit was the measurement and the substance, and in those cases, the measurement, okay, was a standard measurement. It wasn't that big of a deal, but the substance was really long because it was molecules of something. It was atoms of something. So we said, well, that's really hard to deal with, so we condensed it into those weird words. Okay? All we did was do a shorthand of what that unit was. Okay, that entire unit. Okay? So that's fantastic. I like that first step. Okay? The next step is evaluating the information given to us. Okay? In Unit 2, we tend to be given all of the information we need. There's some kind of gray areas like the metric system conversions. We aren't given those because we're expected to know those. Okay? When we move into the next section of material, you're going to be expected to know where to find some conversion factors. Okay? But we can look at our given information, and what I would argue we should do would be box that given information. Okay? Officially, I should be boxing the acid there, so let's go ahead and just do it. Okay? And that and there. So this is two distinct pieces of information. So if I'm going to now insert these things into my solve, I should not be inserting them into the same space or the same block, because now I'm crossing two pieces of information. I want those two pieces of information in their own kind of section within my solve. Okay? Which of those two pieces of information do I want to work with? So now we have a rhetorical choice. We get to decide which one to use. Okay? And I can tell you the majority of people solving this question will start with the 1,275 milliliters of acid. Okay? And the question that I ask those people is, well, why did you start with that? It's the first thing that I saw. That's a pretty crappy decision, because all I have to do is now switch the order of the given information and you get the question potentially wrong. Okay? So you have to have a better rhetorical reason. Okay? What is the rhetorical reason we've talked about?
Because the instructor likes to trick you. And
so do the opposite. Well, if we do the opposite, that doesn't work either. Okay? So you can't just say the instructor's going to trick me, so I'm going to do the opposite of what looks obvious. That doesn't work.
You want to see what you want, and then basically put that in the numerator.
What do I want? Okay? And where do I want grams? In the numerator. So I'm going to go back to my given information and say, well, where does grams show up in my given information? That's the piece of information I want to use first. Okay? Not only is that the piece of information I want to use first, but I want to make sure that when I bring that down into my solve, I'm placing the unit exactly where I want it to be in the answer. Okay? So I go up to my given information, and we can start with our 1.84 grams per milliliter. Okay? Where do I want the grams to show up when I bring that information in? I want it to show up in the numerator. Okay? Give me just a little bit of a second here. Okay? Am I given just grams?
No.
I'm given grams per milliliter. So someone pioneering enough, thank you, okay, could go through and write it like this, which is sort of okay, and we'll address what the issue is in just a second.
I don't know if I missed this, but why did you put it like right by the,
So the sequence in which we write this is kind of up to you, okay? Admittedly, I am switching on you. Typically, I write it to the extreme left. I've started to realize that I don't have to write it at the extreme left. I can start it at the extreme right, and in that way I can slowly build it out, and then I don't have this empty white space. Okay? I'm changing my rhetorical porpoise behind this, because dolphins are just weird.
How you're writing it.
Okay? It's really just changing the structure a little bit on the placement. Why? So we don't have that empty white space. Okay, that's it. It's entirely up to you if you want to do it that way. Okay, does that make sense? Okay, the number that gets associated with this? 1.84. Because I've got my grams in the numerator, I know the 1.84 should show up next to the grams. So I could go through and write 1.84. Okay? Because we've talked about it, we could say, oh, well, we put the 1 here. And before we start panicking and saying anything else about this, let's just kind of process this out a little bit. We look at it, we see milliliters, right? Do I want milliliters? No. Okay? So the next reflex is to say, okay, I need to include something else in here to get rid of those milliliters. Well, where do the milliliters appear? Where does it look like they appear? In the numerator. So in your very next step, where are you going to place milliliters? In the denominator. Okay? For those of you looking at your work, is that what you did? No. Well, what the hell? Okay? Remember when I said that slash? That slash was only an artifact, if you will, of the technology. The technology doesn't like showing fractions, so it shows as a slash because that's easier to type. That technology is not there to help us solve. It's there to help us write it. When we go through and do the solve, what we need to do is acknowledge what that slash means. That slash means put it in the denominator. This isn't 1.84 grams per milliliter all up in the numerator. This is 1.84 grams per 1 milliliter. Are my units going to cancel? No. Okay? So because I followed the technology and ultimately the failures of the technology to hide the knowledge, okay, I also end up failing to solve the question. Okay? So we have to be careful that when the technology gives us that information, we do have to make some interpretations. So when mathematicians say, well, you shouldn't just rely on calculators, the reason we shouldn't rely on calculators is not because calculators do calculations wrong. It's because
Humans do calculations wrong.
humans entering the calculations into the calculator do calculations wrong. This is why we have to understand what we're putting into the calculator, not just punching random buttons on the calculator. The calculator is not going to screw up the calculation. If you're getting something wrong, it's not because the calculator didn't do multiplication or division right. It's because you told it to do the wrong thing. Okay? That, what you're telling it to do is this process, is this work. That's why you have to set it up. Okay? So we have to be careful that technology doesn't screw us over. All you got to do is watch all the sci-fi movies out there. Right? Okay, so with the proper writing out of that first unit system, what happens? We would know that we've placed the milliliters in the wrong place because we need the milliliters to cancel. Milliliters need to show up in the numerator. Am I given just milliliters?
No, you're giving 1,275.
Okay. When I'm asking, am I given just milliliters, what am I asking? Are you given something that has just the units of milliliters?
Yes.
Yes, that's all I'm asking. I don't care what the number is. Am I given just that unit, sitting its own useful piece? Yes, I am. What is the numerical value associated with just that milliliters?
1,275.
Now when I look at the work, what happens? Milliliters will cancel. What unit would I be left with? Grams. The end result is I get 1275 times 1.84. Now I'm done. Okay? There are people that will go through and say, well, couldn't you have said density equals mass over volume? Since I'm solving for mass, it's just density times volume. Yeah, absolutely. I memorized a chemical, or not a chemical, I memorized a formula to do that calculation. I don't have to memorize any formula. The units will take care of it all for me. Okay? Kind of makes sense? Okay. And because I like what Greg did on the upper right, that side of the classroom, what we're going to do is a couple things. One, I'm going to direct you all to it, and we're going to test my ability. Hopefully this is not a selfie. Cool, it's not. We'll take a picture.
Didn't finish.
Yeah, it's close enough.
I like step 1. What is our God?
Nice. No. But that's a good question to ask.
Okay. And if I'm correct,
God in this angle.
what will happen is that showed up now in our recording. I can clear everything away, and we can look at... Do I want to clear everything away? Yeah, we're going to have to clear everything away. Not that way.
You're only as smart as you make your technology.
Exactly right. Fair point. Okay. Use photo, and we can look at it, and we can decide, is Greg's aspect for how he's gone through and set this up work? Okay, so what was our first step?
What is our goal?
Where were we going? So what did we do?
We put grams.
We put grams. That's where we're going. The next part was evaluate the information that was given to us. Okay? So in the case of what I went through and did is I but I drew boxes around the given information. Okay? Oh, which he's actually writing this step too.
Yeah, sorry.
Start B.
It's not quite there.
See, make that choice. Make the decision of which one you want to use, and make sure your logic behind that is a sound piece of logic. Okay? It's not just the first piece of information I see, it's why am I choosing it? I'm choosing it because grams is what I want. So that unit showed up, so now I'm going to go through and use it. Once I've got that rhetorical decision, I can now insert it into my solve. Okay? Develop a sequence of calculations. Okay? Well, really what step 3 is, repeat step 2a. Okay? Evaluate the given information. Does it match? Or evaluate your equation. Does it match what you want? If it doesn't, go back. Look at your given information. Insert the given information in to make it match. How many times do you have to reevaluate step 2? Depends on how many different pieces or steps of calculations you have to go through and do. Okay? In this case, it was 1. In some cases, it could be 3 or 4. Right? So you have to continually evaluate back to that given information. One of the things that's going to be tricky is in the next unit, that given information could be limitless. And it's limitless because we have the periodic table. Okay? It's limitless because we have a chemical equation. We have chemical formulas. So that given information now has to be interpreted from some of that other stuff. Okay? So when I tell you H2O, you can tell me how many hydrogens? 2. That was a relatively simple concept that you already knew, but what you're doing is using the chemical formula to come up with those numbers. Okay? To come up with that conversion factor that you can now insert into your system. Interestingly, 2 hydrogens equals 1 water. What did we convert? Was it a measurement? When I said 2 hydrogens equals 1 water, did I convert a measurement? No. What did I convert? I converted the substance. I went from hydrogen to water. That's a substance change. Using chemistry, we're looking at substance conversions. Right? The measurement conversions, that's all your old school mathematics stuff that you should have already had. Okay? Depending on how you were taught that, you may not have those tools. That's why we spend the time to go through and look at them. Kind of make sense?
Absolutely.
Okay. So now that you're starting to get a grasp on that, let's go ahead and switch up topics entirely and switch to temperature. Okay? Temperature is another measurement system. Right? There are three main measurement scales. We've got Fahrenheit, Celsius, and Kelvin. Why do we have three different scales?
One's ours, one's something else.
One's ours, one's something else, and one's something else. Okay? What are our measurements for mass?
Our measurements?
I'm intentionally being vague.
We use pounds.
Pounds, grams, are those the same unit system? No, that's imperial versus metric, or American versus metric, because we're the only ones that freaking use it. Okay? Why? Those systems were created with enough historical content and then enough historical backing by people supporting them that they were never removed from the system. We're now so far into those systems technologically that we aren't going to be able to break away from that. Same thing is now happening with our temperature scales. Maybe arguably our temperature scales could be broken from because I don't think we quite have that technological power driving them. Okay? But we still have this system. So Fahrenheit, okay, when we looked at Fahrenheit, our common numbers is water freezes at 32 and boils at 212, okay, degrees. Why were those numbers picked? Why did we pick 32 for the freezing point of water? Just because. That's when liquid turns into a solid? Okay, that's cool. What did Celsius pick? 0. Why did Fahrenheit pick 32? Isn't 0 a more sensical place to start? They are different units, but why were those different units created in that system? Okay. Celsius picked it because water was the most common substance. We get solid water, we get liquid water. We can then reference those as zeros and hundreds. Why 100? 100 is an easy number to deal with. That metric powers of 10 kind of deal. So we can say, oh, we'll just scale it off of water. And we're going to make the assumption that the rest of the world follows water. Is that true? No, it doesn't. It doesn't follow it at all. Which is why when we look at that system, we get all sorts of other weird numbers, like negative Celsius. Fahrenheit actually took that into mind. He said, negative symbols are crappy. I don't want to deal with them. Why did he pick 32 degrees Fahrenheit? Because Fahrenheit, the scientist, lived in an area where he noticed that we could get to temperatures lower than the freezing point of water. He didn't want to use a temperature scale that would get negative numbers. He was in a system that he knew I could be colder than ice. Okay? What was his coldest temperature? 0 degrees. He could get to negative 32. He didn't get any colder than that. Okay? So he knew he could get colder than ice, so he created a scale that would allow him to show that marking. That's pretty cool. Okay? Unfortunately, both Celsius and Fahrenheit have some massive flaws, because in both cases, I can get lower than the 0 point. For Celsius, we already know we have a lower 0 point because Fahrenheit exists. Okay? And Fahrenheit picked 32 so that we could get to 0 as our coldest point. Okay? With enough science and technology, we could realize that we can actually get lower than both of those. Okay? And this is where science stepped in and measuring out temperatures or defining those ranges to realize that there is an absolute 0. There is an absolute mathematical lowest temperature. Okay? And that is going to be 0. And we pick that as our standard point, and we don't have to worry about negative signs then. That's phenomenal. We don't want negatives. Right? That new scale then requires a conversion out with all the others. Okay? That scale was then based off of Celsius, probably because Kelvin was used to using Celsius and so used his conversion between Celsius and Kelvin to match that. So when we look at Kelvin, our common water numbers, it freezes at 273 Kelvin and it boils at 373 Kelvin. Okay? Anybody notice what's different between Kelvin and Celsius? Just 273. 273 to 0, 273 to 100. There's our ranges. Subtle typo here. This is not degrees. Both Celsius and Fahrenheit are actually degrees. They're arbitrary measurements off of an absolute or off of their scale. Kelvin is not a degree measurement. It's an absolute value. So they aren't degrees Kelvin. It is 273 Kelvin, not degrees Kelvin.
Is Kelvin universal or is it just for Earth? Like,
It's for physics.
I mean,
So it's for physics as we know it.
but like, do we have the technology to know that there's this?
So with the mathematical system that we've got, we should not ever be able to achieve absolute zero, because that then causes all of our physics laws to crumble into nothing. Okay? So why do we trust Kelvin to be an absolute scale? Because we have physics laws that we know work. Okay? And we've proven that they work within a high degree of accuracy. So that would suggest that the Kelvin scale makes sense. Okay? That we can't achieve that zero, because then the laws of physics fall apart pretty heavily. Like that would be earth-shattering if you could get to that. Right?
So it doesn't mean no one. Yeah, it doesn't mean it's.
It doesn't mean it doesn't exist. It just means we have no reason to believe that it would.
I
Okay?
think that's an end of the world type situation at that point.
Well, and it's.
I think there's all sorts of fun philosophical things. I actually wrote a short story kind of about a scientist discovering absolute zero, and then I got laughed out of by my quantum physics teacher. But
So like, since we like, there's no physically there's like no way to achieve absolute zero. It's not actually absolute zero. It's a theoretical.
it's a theoretical absolute zero. So we can get infinitesimally closer to it. It's like a limit.
So we reached like a limit, like 200 or 150 or something.
When we look at kelvins, we've gotten, and this opens up a big can of worms. If you look at how we've approached Kelvin, I think we're down to like 0.04 Kelvin. So we can get pretty damn close to it, but it's not officially absolute zero. The question that I put forth to my quantum teacher, since you've kind of pushed this, is how would we know we've achieved absolute zero? We would have to measure it. But the only way we measure things is by bringing in a substance that also has motion. One of the rules when we hit absolute zero is what happens to motion. It stops. How do you measure no motion if you don't have motion to detect no motion?
You're confusing this side of the room over here.
So it's this weird thing, okay? That's why it would cause a really big earth-shattering kind of aspect behind our laws of physics. All of our laws of physics would have to change if we could achieve that. My question is, how do you measure that if you have no way of measuring it? But again, I don't know the technology behind how you would measure that.
So based on our current understanding of the world and the tools we have available to us, we can say that it appears that this is the case.
Yes.
And the potential to go beyond that, we would have to have new tools or new knowledge or new understanding to prove that. Or
I'm going to sort of caveat that.
Yeah. Yeah. Well, that's science.
Well, yeah, but we have to make assumptions somewhere, always. Right? And that's ultimately how we've made advances. Is someone made an assumption, made some awesome conclusions that were good, but then something didn't work. So what happens? Someone goes back and says, well, your assumptions were invalid because of this. If we fix that assumption, now I'm even closer to the result. Okay? One of the big things that's causing this, or trying to figure out what's happening there, part of this, okay, is the quantum physics versus mechanical physics, okay, or gravitational physics. Those two worlds don't overlap well. That's one of the things that we have string theory for, is trying to explain how they overlap appropriately. Right? We don't have a good explanation because the rules of quantum physics don't match well with the rules of gravitational physics. Right? And that's why you take whole courses on quantum physics. Right? And just because we've pushed this a little bit, interestingly enough, we have proven mathematically to achieve negative kelvins. Mathematically. And theoretically with an experiment to show that, without passing through zero. Welcome to quantum mechanics. Yeah. Right. So quantum mechanics is a weird thing with electrons, okay, and we'll kind of address this without passing through zero. Okay? Electrons can jump from, and that's because we're used to a linear logic. It's not linear. When we think about electrons don't move in straight lines, they jump. I can have an electron exist in one space and somehow make it to another space without existing in between. Okay? And for those who are going, that's crazy, that can't possibly exist, welcome to quantum mechanics. Okay? We have the mathematics and the science to back up that that must be true. Okay? Electrons can tunnel through spaces where nothing is allowed to exist. It's really neat.
Aren't there elements that have a freezing point below
Bel-
zero?
No.
Oh, there are? I thought there were.
No.
So I thought some weren't possible.
Some, and actually I might have to check on that one. Okay? That we may not achieve a temperature that's low enough to get them to solid. I'm not positive on that. I think most do solidify. Because I'm pretty sure hydrogen and helium can be solidified, but you're getting into that 0.04 range.
Anytime you
So-
ask me the substance of a chemical, then I'm just putting solid. At some point it will get there.
So, the phases, because you brought that up, the phases that we talk about, when we talk about the phase for most elements, what temperature are we referencing? The standard temperature, which is also all sorts of weird. Really what we're referencing is actually not standard temperature, we're referencing room temperature. Okay, what is room temperature? That's an entirely different debate. Let's not push that even worse. We're already enough off track. You're going to be responsible for dealing with temperature conversions. Okay, the bottom one you need to memorize. To get to Kelvin, it's degrees Celsius plus 273. What is pi?
4.5.
Okay, so 3.1415. I think, James, I agree with you. It's 3.14. Why are Madison and Robbie saying 1.5?
Because that's what it was taught in high school.
Because they may round out the next digit.
They've decided to memorize more digits. Why? Because it probably makes them feel smarter.
No,
273.15. Why the 1.5? That's my smarter moment. I happen to memorize a couple extra digits. That's it. You're not responsible for the 0.15. It's just whenever I write this, I write 1.5. It's just my reflex. Okay? And it makes me feel that much smarter. Which isn't that difficult. But if we go back up to our degrees Celsius and Fahrenheit, I will give you the top one. The second one I expect you to derive. Okay? Derive how?
math.
You convert it.
It's just algebra of the original. Okay? Do you want practice? Sure. There you go. 2 minutes. And arguably less than 2 minutes. Probably push it closer to a minute. Behind it is just a question of kind of plug and chug. Admittedly, I asked you to do it before I erased the easy answer. Because really all you have to do is just plug into that original equation. Okay? I did switch up the question also after the fact, which was a bit silly. Switch it up to be temperature in Kelvin and degrees Celsius. This subtle change usually results in this as an answer. The Kelvin is 98.6 plus 273. I can't do that math, but if we did that math, we'd get a number. Is that the correct answer for the Kelvin?
No.
No. Why would somebody do that?
Because they combined two different.
Okay. They read the question and said, well, if I was given 98.6 degrees Fahrenheit and Kelvin was asked for first, that must mean I'm adding 273 to the Kelvin, or the number 273 to the degrees Fahrenheit. Because why would we switch up the order? We would switch up the order to test, do you actually know what you're doing, or are you just taking the first thing that shows up and plugging it into a formula? Okay? This is an aspect, again, of that rhetorical choice. Why are you doing the solves that you were doing? Is it because it's the first thing you saw, and you just assume that we're gifting it to you? Okay? Or are you using the correct process behind that logical thought? When we solve for Kelvin, it's 273, that's good, but I need degrees Celsius first. Okay? So I can't solve for the Kelvin first. I would have to solve for the degrees Celsius. I can't solve for Kelvin first. I have to solve for the degrees Celsius. Okay? If I set this up properly, it would be degrees Celsius, 9/5 plus 32 equals our Fahrenheit. Our Fahrenheit was 98.6. Okay? I now have to do the algebra to solve around, and I get the degrees Celsius equal to 37. Once I know that, I can sub that in up here, and I get what, 298? I always screw that up. 310 Kelvin. So I get two answers, 310 Kelvin. I see your hand, give me a second. I might know where you're going with it, which will be frustrating for all of us. And not because your question is bad, it's a good question potentially. What do you got?
So I did it the other way. I did Fahrenheit, then I did the 98.6 minus 32, and then 5 over.
So
9.
pause. How did you do that?
I did the other equation.
What other equation?
The other one that we're supposed to memorize.
Are you supposed to memorize it? No, you're supposed to derive it from this one. So that's why I said to solve it out this way. That's why I screwed up, because I let you run with it before I deleted that information. I should have deleted that information.
Still got the same
Okay.
answer.
Why will you still get the same answer?
It's the same thing.
It's the exact same thing. You absolutely should get the same answer. Okay? Should you memorize that other equation? No, because you're given this one. All you got to do is the algebra to switch it around. Are you responsible for doing that algebra? Yes. Can you do that algebra?
Yes.
Then don't memorize the other one. Okay, that's all I'm saying. Okay, so that's not the question I was expecting. That's okay. Still a valid one.
Expecting.
What do you guys think? You want a hint?
Yes, please.
Sig figs. I don't know how to answer that question.
He doesn't.
So don't worry about it. Don't worry about sig figs when it comes to temperature. Okay? It gets a lot messed up here because is that 32 absolute? Is that an exact measurement or is that sig figs?
Is that? We don't know.
Yeah, I don't know. I honestly don't know. Okay? Sorry. Okay? And so because of that, don't worry about sig figs when it comes to temperature conversions. Okay? That said, if this didn't come out to exactly 37, don't give me 37.123953426 whatever. Okay? Just give me 3 sig figs at most with your temperatures and you'll be fine. Make sense? Yeah? Okay. Cool. So, heat concept. We just talked about temperature. Temperature is the average kinetic energy. It's a way for us to measure how much energy is in our individual particles. How much are they moving around? But it's an average of it. Okay? Heat is the measure of the total energy. Okay? So they're both measuring something similar, but from a slightly different perspective. Okay? If your grade in the class is a 70%, does that mean you only have 70 points?
No.
No, it would depend how many points are in the total for the class, right? Okay? So that's the same thing that's happening here. Temperature is that percentage. Heat is the total points. Okay? This becomes really important, say, if you read the old practice exam. Actually, I don't know if it was in exam 2, the practice exam 2. It's for sure in practice exam 3, I think. About a drop of coffee versus a cup of coffee. Okay? How many of you are going to freak out when a drop of coffee hits your skin? Yeah, you're probably okay. But if I take a pot of coffee, the exact same temperature, are you going to freak out?
Yeah.
Why? They have the exact same temperature. You're getting more on you. You're getting more heat transferring into your skin. Because each of those particles is contributing a heat to your skin, with more particles means more heat transferred into you. You're going to care a whole lot more about the pot of water than a drop of water, even if they're at the same temperature. Okay? That's kind of the difference between our average and the absolute energy value. Okay? Because they're different kind of concepts, sort of, we have different units. Heat is often expressed in either joules or calories. Why two different unit systems? Because unit systems. That's just the way it works. Okay? Because we have two different unit systems, though, what could you be expected to potentially do?
But you want to convert them?
You could convert between them. Don't worry about it. We aren't going to do conversions between them, so don't stress. Okay? Our conversion system between them, okay, 1 calorie is equal to 4.186 joules. Okay? That is our conversion system between them. Why would we have picked calorie to measure our energy? Okay? Well, if we look at the specific heat, the amount of energy I need to add to a substance, okay, and in particular 1 gram of substance to go up by 1 degree Celsius, that's the number associated with it. So why was calories picked as a unit? Well, when I take the most common substance I would work with, that would be water. If I look at the amount of energy I have to add to 1 gram of water to cause it to go up by 1 degree Celsius, I can define whatever that energy is as 1 calorie. I get to define my unit system. And because that now gives me a magical, easy number to work with, 1, that's why I define my calories to be based off of that system. Joules is based off of a different system than water, which is why we get a goofy, weird number to go along with joules. Okay? So because of the origins of those units, we see slightly different measurement systems that come out of it. Okay? What I want you to get out of the specific heat, though, is to realize that every substance has a specific heat, just like every substance has a density. Okay? And we can use that specific heat to identify the compound. Okay? We can use it also to make broad, sweeping comparisons between groups of elements, okay, to draw conclusions about them. Which of the following substances is expected to have the largest specific heat? What does a large specific heat mean? Which of those would be a large specific heat? 300 joules or 3 joules? 300, because it's a larger number. What does that number mean? Okay. For me to get a gram of the substance to go up by 1 degree Celsius, I have to put in 300 joules of energy. In the other case, I have to put in 3 joules of energy. So I put in less energy and I get the same temperature change. So if I have a large specific heat, I have to put in tons and tons of energy into the thing to cause it to go up by 1 degree Celsius. Okay, so big amount of heat, small change. Right, and now we have a list of elements. Okay, is there a property of our elements that we could tie to specific heat? Okay, in this case, I'm putting in a ton of heat, and it doesn't change a lot. What could I describe of that substance? What is it doing with that heat? It's absorbing it. So if I touched my hand on it, right, would that be a good thing for me to use for a hot mitt or a hot glove or a pot? Right? I put in a ton of energy and the temperature doesn't go up. Is that a pot? The whole point of a pot is I put it on the stove, I put in a ton of energy and it doesn't get hot. Is that the point of my pot? No, what's the point of my pot?
To get hot.
To get hot. So I put in a small amount of energy and what happens to the pot? It gets hot. Okay? If I put in a ton of energy into the glove, what's the whole point of the glove? To not get hot. Why?
Protect you.
To protect my hand. We're talking about the glove being, begins with an I. Mune's not a bad response. An insulator, and the pot being a conductor. Okay, what was the pot made out of? Metal. What was the glove made out of?
Rubber, probably.
Rubber. What is rubber made out of?
Silicone.
Okay, it's not silicone. That's silicone was the first answer, but that works. Silicone. What is the difference between a metal and silicon? What is silicon? It's the metalloid nonmetals. If we look at organic materials, that's carbon, which is nonmetal. So a large specific heat is an insulator. A small specific heat would be a conductor. What materials are conductors of heat? Metals. What materials are insulators of heat? Nonmetals. So really, what is this question asking? Which of the following substances is expected to be Which one of those was our largest specific heat? We got the work up there. The nonmetal. So which of the following substances is a nonmetal? Carbon. Is that a really easy question to ask? Yeah, that goes all the way back to Unit 1. Which of these is a nonmetal? Okay, knowing what those physical properties are. Okay. That said, is this also a very difficult question to ask? Okay, largest specific heat. We're like, what the hell is that? I don't know what that is. You have to break down the meaning of what those things are. Once you've got the meaning, you can make it into an easier question. That's what you're doing with all questions you're encountering. Even our conversions. We're saying, I want grams. Well, I wasn't given grams. How can I rearrange the information to make it so that I eventually get to that piece of information? All you're doing is changing the question into something that you can answer, but by making small logical steps that are easier for you to process. That's the point behind this. Make sense? Kira, you had a question.
I feel like this probably goes beyond our class, so this might be valid. But what if there was two nonmetals?
What if there were two nonmetals? Would I ask the question? No. Right? The trends in specific heat are a lot more complicated than what we just addressed. Okay? This is a general processing technique that works, and because it works, I'm using it on the test. I still go through and verify that the specific heats all perfectly align up to match this. Okay? I could change the question to be the smallest specific heat. If I switched it to smallest specific heat, that's now asking for you to answer. Which one's the metal? Can I leave all those answer choices? No, because now there's a whole bunch of metals there to choose from. I wouldn't be able to do that. So if I switch it to smallest specific heat, what happens?
You have to change your available options, right?
I change the available options to now be mostly non-metals, and you would identify the one metal. Make sense? Okay. What's the extra layer of crap put behind this question? No, the expected to have is still trying to go off of that trend.
Largest specific heat.
That's how we started this whole process. You're like, dang, well, that's the whole question. Is it just a question, or do you also have answer choices to choose from? When you're trying to decide metal and non-metal, what are you looking at? The side of the periodic table. Find copper as a word written on the periodic table. What's the extra layer of crap behind this question?
Copper.
You have to
know the element name.
You have to know all the way back to Unit 1 the name of the elements and how it ties back to their individual symbols, because you're using the periodic table to do that translation. Right? So a single question can get at multiple tiers just based not in just the question, but also in the answer choices. This is why multiple choice can be tricky. We can force multiple aspects of knowledge on you without you recognizing it. Make sense? Cool. I thought Suf had a question, but maybe we'll come back. We good with that? Cool. After specific heat, we get into some concepts that we've already dealt with. The law of conservation of mass. This is how we balanced equations, believe it or not, was based off of the law of conservation of mass. Okay? So we've got a couple equations down here. How could we mathematically use this? If I give you 2 grams, that's the wrong button. if I give you, now the cursor's bugging me. If I give you 2 grams of hydrogen, 1 gram of oxygen, and I assume the law of conservation of mass is correct, don't worry about balancing anything. Everybody watching at home, oh my God, hold your freaking horses. How much water is produced? What does the law of conservation of mass say?
Mass is neither created nor destroyed.
Okay. So through a chemical reaction, I cannot create more mass and I cannot lose mass.
So it'd be 3.
Which means the mass of water at the end of this has to be 3 grams. Okay? That's the law of conservation of mass. That's all it's saying. Okay? So let's make it a little bit harder. I give you 2 grams of wood, 1 gram of oxygen. How much water did you produce this time? Okay, I heard a suggestion for 2. Has anybody been like, well, that was a crap question. I don't know how to answer that. Okay, who's saying it's a crap question? How can I answer that? Why?
Because there's no hydrogen to go with oxygen.
Interesting point.
And the product is like 2 things.
The wood is an organic material composed of carbon and hydrogen, so unfortunately your point is invalid.
Isn't it because of the gas? You can't really measure the grams in the gas.
The law of conservation of mass says the total mass on each side must be equal. So water could be 2 grams. If water came out at 2 grams, you're then saying the gas was
1.
1 gram. Couldn't it have been 1 gram of water and 2 grams of gas?
Yes.
Couldn't it have been 0.5 grams of water and 2.5
Yes.
grams of gas? How many possible solutions are there? An infinite amount of solutions. So based off of the given information, can we answer that question? No. So law of conservation of mass does not say that masses always match out. We have to be very careful with the information given and not overuse it. Okay? If your reaction has 2 things and ends with 2 things, I'm not going to be able to predict the mass of one of the products. Okay? At least using the law of conservation of mass. I'd have to bring something else in. Okay? Kind of make sense? What if I wanted you to actually tell me what the mass of water was? You have to give me an answer. What do I also have to give you?
You have to.
What do I have to tell you so that you can tell me the mass of water? I also have to add in that the mass of gas was 0.5 grams. With that extra piece of information, you can now use law of conservation of mass to say that the mass of water is 2.5 grams. And now you can answer that question. Does that make sense? Okay. Total mass on both sides. Okay. Typically, when you see questions about the law of conservation of mass, almost universally, they reference equations like the one above. What kind of reaction was that? A combination reaction. Because we can say, I give you these 2 reagents, how much product is made?
1.
I can determine that. There's only one thing in a combination. That's where the law of conservation of mass is typically centered on. So when you see questions on conservation of mass, think about the rhetorical choice given by the author. Is the author giving you all equations or only one particular type? Typically, they're only giving you one particular type, and it's a combination because it matches really well with the law of conservation of mass. Do not use the law of conservation of mass on other equations if you're missing information. Okay? Einstein came along, figured it all out for us, and said that mass and energy were directly tied to each other through his famous E equals mc squared. Okay? Which means if I have the law of conservation of mass, I thereby extension have conservation of energy. Okay? Those 2 laws we can tie together in one big grand thing and say we have the law of conservation of mass and energy. Okay? But they're 2 separate discoveries. okay, that we then tied together through Einstein. We do get a chemical, or not a chemical, a mathematical equation, which means we could be asking you to do math. I don't care. We're not doing it. Okay? If we look at the law of conservation of energy, this is probably the largest reason why we have science to begin with. Okay? Why do biologists study plants?
Because they want to know about the life and you need it.
Okay, so we could evaluate looking at life and eating it. What else do plants do?
Give us oxygen.
They give us oxygen. What else do they do?
They are
Medicine, antibiotics.
Where do they get the energy to exist? Do they consume other life?
they take our breath or whatever it is.
They get it from the sun. How do they do that?
Photosynthesis.
Okay, that's pretty cool. I wonder if I could do that so I could put lights in this room. That would mean I need to do something like plants do, and I need to research solar energy or photosynthesis. I can look at what the plants do and convert what the plants do into something that I can use to put lights in my room. Okay, why do I want lights in my room?
So you can see.
Okay, well, isn't there a freaking light outside right now?
Yeah.
Yeah, why do I need a room? There's no sun in the room. Why do I have the room?
We're basic humans who need shelter.
To protect you.
Why do we need the shelter? Because in this particular location, the sun also generates
Heat.
a significant amount of heat, and it makes it unbearable to live outside. So we build shelters. But as soon as we build shelters, what do we have?
No light.
No light. I can't see. So what do I need? I need light. So what do? I invent fire. Ha ha, I can now see. But now what does the fire generate? Heat. That turns up my room really hot. Dang it. So what do? I create a different energy system, electricity. So that generates the power somewhere else, and the electricity can be driven into my room to turn on the lights so that I can now see within the room.
And there's no heat involved.
Okay? Is there no heat
There's
involved?
a little bit of heat involved.
There's a little bit of heat. Okay? So what I'm doing is looking at different ways to convert those different forms of energy to get them to do something that I want them to do. In the result of that, all sorts of other things happen. Law of conservation of energy, I don't get a perfect exchange of those energy forms, which means I always lose a little bit. I'm not taking advantage of all the electrical energy to make light. Some of it is being turned into heat. What am I doing with that heat?
Nothing.
Arguably, actually, what I'm doing with it is building another system to remove the heat so the room stays cool. But at the same time, what does that instrument now produce?
Heat.
A whole bunch more heat. Okay, so we start getting all of these little losses. It's that efficiency loss that a lot of our engineers are trying to solve. How do we create a system that transfers that energy better? Okay, so we're transferring from one form of energy to another so that we don't have to do as much work. Okay, or I can be more comfortable. To get here to this room, what did you do? You drove. How did the car work? Gas. What was gas?
It connected to the engine causing heat.
What is gas? Come on, what class is this?
Form of energy.
I'll accept that, but come on, what class is this?
Chemistry.
Chemistry. What is gas? A chemical. What are we doing to that chemical?
Burning it.
We are exploding it. We're exploding it in a very small amount so that what happens? It moves a piston. What does the piston then move? The car, and we get motion. Okay? We're using chemical energy to convert the motion or the chemical energy into mechanical energy to move the car. But at the same time, what happens to the engine? Have you ever touched the car afterwards? It gets hot. Did we get a perfect transfer of energy into motion? No, we lost some of it to heat. Okay? We're losing that energy. So we try to create other systems that allow us to get through that better. Okay? Ultimately, what we're talking about is the 6 different forms of energy and how we can transfer between each of these. Every transfer between generates heat. Okay? To get light in this room, the best and absolute source is remove the roof. I now have light in the room. Okay? The problem with that is I now no longer have the shelter. Okay? So I would have to sacrifice that. Okay? If I bring in the shelter, now I have to somehow get the energy into the room to cause the lights to come on. That could be electricity. Where did I get the electricity from? What's that?
Lightning.
Most of the lights in our room are not powered through lightning.
A little?
There might be some very small percentage powered through lightning.
Isn't it through copper wire and something else?
The copper wire is not generating electricity, it's allowing the electricity to move to here.
Like wind, right?
Okay? We could look at wind power. We could look at the wind causing a mechanical rotation. That mechanical rotation is translated into electrical energy. That electrical energy makes it to our place. So we're going mechanical directly into electrical into light. That's a pretty short loop. That's pretty cool. Is most of our energy coming from wind?
No, most of it comes from water.
Okay? In Arizona, we get a significant portion from water. So we just throw water in an engine and it generated electricity? Right? We take water from a high altitude. What does the water at a high altitude do? It falls. As it falls, we make sure it moves through something. What does it move through?
Probably one of those
Effectively the same thing as a windmill, except
water power.
for water. So instead of air pushing a turbine, it's water pushing a turbine. That generates electricity. The electricity now can be transferred to here. Okay? Is it all your question first?
Oh, sorry, I have a question that's kind of stupid, but like, you know, electric cars, does that help preserve heat as well? Because I know that it preserves like gas and all that stuff, but like,
So if you touch an electric car, do they get hot?
I've never touched one.
Yes, they still get hot. It's a smaller heat loss.
Okay.
So yes, it's there, but how did you get the electricity into the car?
Power.
If you're getting it from wind, cool. If you're getting it from electricity, cool. Or it's not electricity, water, cool. Where else could you get that electricity from?
Plug.
The sun?
Sun, we could get it from the solar power. The solar light hits the solar cell, generates electric current, and that could go into our batteries of our car. Cool, that's a pretty direct connection. Where is most of our energy coming from? It's not solar, it's not wind.
Some of it is used.
Oil. Most of it is oil. Okay? It's a chemical combustion. That chemical combustion is doing what? We're doing combustion to turn it into mechanical energy. So we're doing chemical to mechanical to electrical to light. Where in the previous cases, what did we do? We went mechanical to electrical to light. We've added an extra step when we look at the combustion of oil, okay, or coal. That extra step is now a heat loss. That's not as efficient. Okay? So we're now losing energy somewhere else. So if we can improve our technologies in those other cases, the ability to trap solar light, the ability to trap water power. The problem with water power is, what do you have to have?
Water.
You have to have water. Okay? And not only that, is the ocean a good place to find that water?
No.
No, because what's the water need to do?
Get desaltified.
It needs to fall. The ocean is the bottom. That doesn't work. The ocean's not falling anywhere. If anything, it's a different
You're
argument.
just flat though.
Okay? We need to put our power points, okay, our turbines, up at higher altitude. So as the water falls, it can cause the turbine to generate electricity. Okay? The water has to naturally do that. If we have to put the water to the top, well, how did we put the water to the top? We had to put energy in. That's freaking burning the power again. Okay, which we've already proven is an inefficient system because in each of those steps, we generate heat. That heat is always a loss. Right? So our biggest problem as far as engineering is, what do we do about heat and how can we minimize that effect as much as possible? Okay? So a lot of what we're doing in science is revolving around those and how we make those leaps. Okay? And that's kind of cool. Okay? And if we think about that even further, okay, we don't have to use it in just doing those leaps back and forth to get light in this room. We could use it to kill people. How does a cannon work? Combustion of gunpowder, which is chemical. We can use chemicals to kill each other. Awesome. Great. The same time, that same process that we're using in the cannon, combustion to launch an object. What are you doing in your car? Combustion to launch an object. Okay? But it's now, how do we control that? Almost all of what we're trying to do is, when it's centered on energy, is it could be used destructively if we don't control it. Hey, you putz. We can use it in a controlled fashion to gather our energy, or we can use it in a destructive fashion if we just unleash hell on it. Okay, we didn't talk about nuclear power. We have a nuclear power plant that generates a significant amount of energy. Okay, that's being converted into electrical. I'm going to have to give him a hard time later, too.
Isn't there water
Okay.
to it?
Sort of. Since no one asked, I don't want to bring that up yet. Okay? So it's chemical energy. Kill. Chemical energy, move. What's over here? Anybody taking any kind of biology class? ATP? Energy. It's the cell or the energy that all life, or not all life, but most life as we know it, uses as the primary currency to transfer energy around. We convert ATP to ADP. T for
Totally radical.
try, D for die. Literally, in the transfer from ATP to ADP, we are breaking one thing off. We're breaking, what was the P? Phosphate. Okay, remember when we talked about complex ions? That phosphate ion? All we're doing is breaking one bond. That single bond breakage gets us enough energy to cause most of life as we know it to exist. One bond. What if we tried to break all of those bonds at the exact same instant?
We'll die.
We would explode. Right? That's how much energy is stored in that. So just like car engines, we're slowly accessing that information. We're controlling it, or that energy. Same thing's happening in life. Slow energy releases so that we can live. Okay? Otherwise, we just explode in a fiery ball.
But that sounds like such a good time.
Okay. Oh man, with only 2 minutes. Kinetic energy. Kinetic energy is a measure of motion. Kinesiology, the study of human motion, right? The body. We look at kinetic energy, it's the study of motion of molecules. We've got solids, liquids, and gases. What happens to the kinetic energy as we go from solid to liquid to gas? It increases. Gases move a lot. That's why they fill the volume that they're in. Okay, why do they move a lot?
Because they can't still.
More kinetic energy. It's literally what it is. We add a bunch of energy in, it moves more. Okay? What happens with temperature? How do I go from a solid to a liquid to a gas? What am I doing? I'm adding temperature. What is that temperature doing?
Adding activity.
Adding activity, also known as
Energy.
kinetic energy. It's the natural transition between those. So all this is really saying is there's a direct tie between temperature and kinetic energy. Okay? They are directly related to each other. Okay? What we're about to move into, but not today, is chapter 8 and 9. We're looking at the mole concept. Chapter 8 is very simply looking at a chemical formula and the existence of a mole. Why do I want a mole? Okay? Chapter 9 is now saying, cool, you know something about moles and formulas. What do we do with compounds? I react them to make something else. What is the meaning of a chemical formula? The meaning of a chemical formula is a way that I can convert substances from one thing to another. That's chapter 8 and 9. We're done with them. Yay! Wednesday is going to be rough with lots and lots of calculations dealing with those odd units. This is why you need to have watched that video, which was like last week. Okay? You should have watched the video on moles so that you're ready to run with our conversions. All we're doing is conversions. Okay? That's pretty much it for the rest of the semester. Just conversions involving moles.